In the second module of organic chemistry, we will cover hydrocarbons and isomers. We will have a look at a few definitions, then also the test for saturated hydrocarbons, and lastly I will show you how to distinguish between the different types of structural isomers. First definition is a very popular definition in the question papers. Hydrocarbons are organic compounds that consist of carbon and hydrogen only. For example, C3H8 or CH4. Hydrocarbons can be either aliphatic or aromatic. Now you will see in some of the textbooks that they do mention aromatic hydrocarbons or benzene rings. We will focus our attention in the CAP syllabus on aliphatic hydrocarbons. These are the hydrocarbons that are open chain hydrocarbons. Now, aliphatic hydrocarbons can be either saturated or unsaturated. The saturated hydrocarbons are the alkanes, and the unsaturated hydrocarbons are the alkenes and alkenes. So what is the meaning of saturated? Saturated hydrocarbons are those organic compounds with no multiple bonds between the carbon atoms in the hydrocarbon chain. There are only single bonds between the carbon atoms. And it's really important that you have to include the between the carbon atoms in your definition. Unsaturated hydrocarbons are those organic compounds with one or more multiple covalent bonds between the carbon atoms in the hydrocarbon chain. So if there's at least one or two multiple covalent bonds, so double or triple bonds, between the carbon atoms in the hydrocarbon chain, then that hydrocarbon is unsaturated. So how do you test practically for a saturated hydrocarbon? Theoretically, you already know that if a hydrocarbon is saturated, it means that there are no multiple bonds between the carbon atoms in the hydrocarbon. But if that hydrocarbon is unsaturated, there must be at least one multiple bond between the carbon atoms in that hydrocarbon. So to test for saturated hydrocarbons, we add bromine water to the sample. Bromine water is a very distinctive dark brown color, but it's also very poisonous and dangerous to work with. Therefore, in the classrooms, we often use purple potassium permanganate as a substitute for the bromine water, which is much safer to work with. When we add bromine water to a sample of a saturated hydrocarbon, the bromine molecules will find it very difficult to find a spot where it can react with any of the saturated molecules because all the spots are taken. So if the bromine remains unchanged, the color of the solution will remain brown. But if the bromine water is added to an unsaturated hydrocarbon, the bromine will very easily find a spot where it can react with these molecules, and new molecules with new properties will be formed. So if all the bromine molecules can find spots where they can react with these unsaturated hydrocarbons, there will be no more brown bromine molecules in the solution, and the solution will lose its brown color. So if we add brown bromine water and the color remains brown, we know that the sample is in a saturated solution. But if the color changes immediately and quickly, we know that the sample is an unsaturated hydrocarbon. A few drops of the brown bromine into the unsaturated solution, and you can see how the brown disappears. But a few drops into the saturated solution and the brown remains. Structural isomers are organic molecules with the same molecular formula but different structural formulas. We will look at three different types of structural isomers. The first type of structural isomers are chain isomers because they have different chains. If you look at the molecular formula of C4H10, then you know that the structural formula must have 4 carbons and 10 hydrogens. But if you look at the second molecule, there are still 4 carbons and 10 hydrogens. So we call this molecule a chain isomer of the first because they have different chains. The second type are positional isomers, and they have the same molecular formula but different positions of the same functional group. So if you look at the molecular formula, the OH, which is a hydroxyl, tells us that this molecule is an alcohol. But that hydroxyl can be on different carbons. So you can see in both cases we have 4 carbons, but the hydroxyl is attached to different carbons. So the position of the functional group is different for the two molecules, and therefore they are positional isomers. The last type are functional isomers because they have the same molecular formula but different functional groups. So if we look at C3H6O2, one way of drawing this molecule will look like this, where you have 3 carbons, 2 oxygens, and 6 hydrogens. So the functional group here tells us that this is a carboxylic acid. But you can also draw a molecule looking like this, with 3 carbons, 2 oxygens, and 6 hydrogens. So the same molecular formula, but a different functional group, because this functional group tells us that this is an ester. So carboxylic acids and esters may have the same molecular formula but different functional groups, and therefore they are called functional isomers. A nice tip: if they ask you in a question paper to identify functional isomers, always look to see if you can find a carboxylic acid and an ester with the same molecular formula. If you can't find a carboxylic acid and an ester, try to find an aldehyde and a ketone, because aldehydes and ketones also have the same molecular formula but different functional groups. So aldehydes and ketones can also be functional isomers. Let us see what you can remember. Consider these two molecules, A and B. What type of structural isomers are A and B? So if you study A and B, you can see that the double bond immediately catches our attention. So the functional group here is the double bond that tells us that A and B are both alkenes. The chains are identical, 4 carbons, and the only difference here is the position of the functional group, the position of the double bond, that is different for A and B. So A and B are positional isomers. If you consider these two molecules, you can see that the chains are different now, because C has a branch on the second carbon. Still 4 carbons, but there's a branch on the second carbon. So the chains are different here, even though they have the same molecular formula. So these are chain isomers. Shortly describe an experiment to distinguish between a saturated and an unsaturated hydrocarbon. You have to add bromine water, and if the color remains unchanged, if it remains brown, you know that the solution is saturated. But you have seen that if the color changes instantly, you know that the solution is unsaturated. Consider these molecules and write down the homologous series of each molecule. We start with A. A has only single bonds between all the carbons and hydrogens, and the functional group here will be the hydroxyl. So the hydroxyl tells us that A is an alcohol. Same story for B. Only single bonds between all the carbons and hydrogens, but a hydroxyl as a functional group that tells us that B is also an alcohol. C only has single bonds between all the carbons and hydrogens. So C is an alkane. The functional group for D is the carboxyl group on the last carbon. So there's a double bond O and an OH on the last carbon, so D is a carboxylic acid. E, again, only single bonds between all the carbons and hydrogens. So E is an alkane. With F, the functional group is the oxygen in the chain of carbons and the double bond O on one of the adjacent carbons. So this functional group tells us that F is an ester. Which of these molecules are chain isomers? Explain. So for chain isomers, we will be looking for molecules with the same molecular formula but different chains. Now E has a branch. So E is a possible chain isomer, and we will be looking for another molecule with 4 carbons and 10 hydrogens, but with a different chain. And C also has 4 carbons and 10 hydrogens with no branches. So C and E are both chain isomers because they have the same molecular formula but different chains. Which of these molecules are functional isomers? Explain. So for functional isomers, I told you to look for a carboxylic acid and an ester or an aldehyde and a ketone. But we already know that we have a carboxylic acid and an ester. D and F are functional isomers because they have the same molecular formula, C3H6O2, but different functional groups because they are part of different homologous series. And then lastly, which of these molecules are positional isomers? Explain. So for positional isomers, we will look for the same functional group but different positions for that same functional group. And we already know that A and B are both alcohols because of the hydroxyl. And for A, the hydroxyl is on the first carbon. For B, the position of that hydroxyl is different because it's on the middle carbon. So A and B are positional isomers because they have the same molecular formula but different positions for the same functional group. If you are an educator that would like to inquire about the use of these PowerPoint slideshows in your classroom, you may contact me at lawsandwonders@gmail.com. Please indicate if this topic was useful to you or not, and subscribe to my YouTube channel in order to stay informed about the release of my most recent videos.